am emoții când în sală este colega de clasă cu care am mers 4 ani spre școală și de la școală la Liceul de Filologie Istorie și profesorul drag cu care m-a învățat informatică. Sunt român, am crescut în Timișoara, restul prezentării va fi în engleză, dar scopul este să începem un dialog. Suntem cu toții egali și sunt onorat să fiu aici. So, I was asked to talk about 20 minutes about what am I doing and what's going on. It's very short time, and if the goal is just to start building a dialogue, Seattle is not that far from Timișoara, and vice versa. Boeing has 2 amazing suppliers in Romania, in Bacău and in Brașov. And about myself, I graduated from the Polytechnic University in '95, and I started a PhD with Tom Dietrich at Oregon State in machine learning. I wanted to do machine learning, and my thesis advisor, Professor Ștefan Holban, advised me to seek excellence in mentoring. I started my career at Boeing in 2001. I had a short stint in the finance industry and came back. And at Boeing, for many years, Boeing is a big company. We have about 160,000 employees over all continents. Machine learning was not as important in 2001 as it is now. I worked on small projects, as it was mentioned. I have my code on computers that read the data from 777 airplanes that come to the gate. We did a lot of surveillance and a lot of research. I'm a humble member of the research community in machine learning. And that's what I want to talk to you about. And I want to talk to you about the hype that is today. You will not hear panicking statements from me. I am a researcher who develops systems, and it's very hard. And I want to share with you today some of those points, and from there we can continue our dialogue. So research in AI, especially in the last 10 years, it's feeding us a lot of great tools. Think of them as the mathematics of computer science, very much like you have a knife. The knives are amazing tools, and the locomotives, right? We have them in our hands, it's the very beginning, and we want to use them, and our imagination goes wild. However, what's useful is actually systems. Systems that work in our factories, systems that work in our home, and more so, we have them already on our phones. How about systems that work in high-stakes applications, such as in our operation rooms, that invest our money, or that fly us or drive us around? So this is a little bit representative of what's going on today. We have some algorithms, and then imagination goes wild. What if we have these tools and they can take over, or they can help us in ways that we haven't foreseen before? However, all these arguments, including Elon Musk's argument, assumes that there is somewhere at least a nugget of a miracle. So how about what is there? And I want to give you 4 points on what are those nuggets. However, remember, the goal is to build systems that make high-stakes decisions. And remember, AI is computer science and it's software. However, systems include hardware, sensors, actuations, interfaces, and so on. So that's why don't be shy if you are a student in mechanical engineering, electrical engineering, civil engineering. You will use these tools, and actually you will be a champion of these tools, so you don't need to be a core AI researcher. Now, I want to talk about the 4 key aspects that may be those nuggets, those miracles, that come from just my experience. And I'm sure there are a few more that you may have. However, I'd like to emphasize these 4 and talk to you briefly about them, and then show you some results that we have. First, we're going to talk about architecting AI systems, then about machine learning and learn models and what do they need beyond making predictions. Then the interfaces with humans that are extremely hard, and then about people, teams, and talent. First, about the architecting of AI decision systems. So most of the decision systems, including autonomous cars, your favorite robot in a factory in Timișoara, your app that provides you the wonderful output from ChatGPT, have a little bit of control, perception, prediction, speech recognition, and so on. And you'll hear about these. They're all together, and they come together. Well, how do they come together? And I work quite a bit in summarizing it, inspired deeply by our work in autonomous systems. And I want you to think a little bit about this. So everything, every system that uses AI has at the center a block that is a decision system, a planning system, and that's the backbone. Think about you having a tool that takes you home. In this planning system, you have decisions on top. You have to be at home by 8 o'clock, and you have to buy a bread, and whatever you have, a date at 9 o'clock, and so on. So that's high-dimensional, low frequency. You don't think about that every 30th of a second. At the low end is your neural actuations, things that you do with a high frequency. However, those are extremely low-dimensional. Those would be the controls on your car. Those would be the controls on the low-dimensional things that can be computed mathematically. It's important to note this frequency and dimensionality trade-off, and we do this for tractability. Aside of this center backbone, we have a lot of perception. So this is our sensing, perception, and so on. And we have knowledge. Most of our systems, knowledge, for example, the maps. The knowledge base, for example, for ChatGPT is all the books that were ever printed and papers and so on. And the perception would be your interface with the user. And then if you have a robot or a system that acts in the real world, you have actuation. So this kind of summarizes, and if you think about an AI system, you should think about the schema always, and about how it's accomplished. If you want to develop one, then you want to see how it's accomplished. And indeed, somewhere in between, we may have humans here right now. We may not achieve all the steps through a computer or a piece of software. Now, in this, you've heard a lot about machine learning. I have worked in machine learning since the times when it wasn't so popular. The truth is that learn models are not end-to-end. And I know there are startups that work on end-to-end driving and so on. I personally believe that they will not be successful. However, we have learn models in special places. For example, for recognizing pixels in an image, for recognizing lines, for recognizing landmarks, for recognizing a letter or an accent that a user has. And that's what I'm talking about when we architect systems. When we work and we develop a system, it is extremely complicated where we have these learn models. And that's what you should have in mind. The second thing is about these learn models. What are they and what's key? And probably you heard about them a lot, and what you see is this prediction, right? Aline said that ChatGPT told them what to say this morning. That was the output. All of them have the output, usually we denote it as a Y. However, to develop those systems, I want to emphasize something that you practitioners want to remember, and you'll you'll see it more and more in our systems. Learning to say, I don't know, and building an uncertainty model about that output. So there would be a secondary output. Aside of the prediction, Aline would have loved to say, hey, this would be my suggestion. However, if your audience has more engineers, this is what you should say. Or I don't know what to say if your audience has politicians or whatever. And that's something that helps us in building robustness in the systems. Think about us humans. If you hear somebody giving a prediction about weather in Baku, instead of being very sure about it, mentioning a level of uncertainty on that brings trust and more confidence in what you hear. And then something that we'll hear more in the research arena, and you'll see it in systems probably in 5 years or so, is doing things in multiple ways. Marvin Minsky, one of the fathers of AI, said, you really don't understand something if you only understand it one way. Right now, in AI systems, we do things only in one way. If we do image recognition, object recognition, we do it in one way. There is a model that recognizes the face of Aline. It's not robust. That system may fail. More and more we see in systems adding multiple systems, for example, to recognize Aline. Maybe I have the lights here and I don't see his face, but I recognize his voice or whatever he wears. So that's something important, and that's something that, for example, in airplanes, you have it. You have redundancy among all electrical, mechanical systems, and so on. So that's a lesson to be learned. Next, I'd like to talk about what we optimize for. And in machine learning, we're very good if we know the function to optimize. That's called the loss function. If you tell me what the cost of the errors are, I can train you a really good model if I have the data. However, in most practical applications, it is really hard, it's extremely hard to specify the entire loss function. Think about you having an advisor, or Aline's advisor in his pocket. He wanted to optimize for an audience for way more than accuracy, than making or not making errors. And that's hard. In practice, how many of you have developed a system, you go to your customer, you have a great demo, and they say, oh, no, but actually, I prefer the system to output something in a larger font, because, you know, or in voice, or in a different way. And that's very important. In many cases, we rush and develop systems and we don't understand what to optimize for. We don't formalize it. There are many, and you'll hear in the audience, speakers today, optimizing for ethics, trustworthiness, good. Well, formalize them in the context of your application, and then it's going to be very easy to build a system that optimizes. So that's the lesson, and it's very hard. Think about an autonomous car. It's very easy to describe how to drive correctly on the road. What's hard is to explain how far can you be off the lane in order to still stay safe. Is it right to turn really sharp to the right or just a little bit sharp? All right, and then data. Data is so important, and everybody will tell you, yes, it's important. Data in real life. Think about your application and the way it's going to be deployed is crucial. And now, that's why we have more apps on the phone, because people use phones and companies can collect data. For cars, airplanes, factories, and so on, it becomes extremely hard. So data in the wild is required. And not only that, it's required from the whole spectrum. So you'd like to see good data and bad data. You'd like to see defects and non-defects and near defects and so on. And so whatever you do, if you have a company project and so on, having a data strategy that enables you to collect this type of data in the wild or in simulation, but you prove that there is an equal sign between your simulation and the wild is key. And don't rush into a project where this step is extremely expensive and you don't have the budget for. Think about it. This is usually the most expensive step. And then, last but not least, so the second to last, human interfaces. Most of these systems have a human interface. Think about how it will be deployed in the wild. You'll have a spoken interface, text interface. If it's a robot, you'll take orders from somebody. In fact, the usability of such a system makes or breaks a product. There are products, so for example, how many of you have heard of the Apple Newton? Apple Newton was a portable device in the 90s which had handwriting recognition at the level of handwriting recognition that we had in the iPhones in 2010 or so. It wasn't ready because the human interface was too complex. It wasn't well defined. And in fact, if you have a product, it's those human interfaces that will define if your system will be successful or not. Think about them carefully and think again. A book that is a big reference for me, David Mindell from MIT has a book, Our Robots Ourselves, in which he describes that if humans are given the right interfaces and the right information at the right time, they can be super decision makers. So, and the last would be the teams, the talent, and the focus. One thing that I learned, and this is true for computer science now more than ever, you have AI roadmaps. Japan just put out an AI roadmap. The US is working on an AI roadmap. I'm sure the city of Timișoara is working on their AI roadmap. Pay attention. Talent is limited. Building those teams, it's extremely limited. Most of those big AI roadmaps are not achievable simply because we don't have enough people to work on those. So at each level, at the leadership of a company, university, county, country, you have to think carefully about what's doable with the talent that you have. And that talent is not only AI machine learning researchers, like many of you. We had amazing successes, and you'll see a project in a second, experts who understand the physics of the problem. If the problem is a prediction in biology, you have to have biologists who understand that, or the AML people who understand those physics. Remember, our algorithms have no idea about the physics and the biology and the chemistry and the physical world. Understanding that is crucial, so when you form teams to build those systems, in addition to your computer scientists, AML people, think about the people who understand the physics environment, and that's where the electrical engineers and the mechanical engineers and the civil engineers have a great role. And then define the problem and focus. It's important to be humble, and that's why I'm here extremely humble in front of you. Systems that you develop make you humble. A demonstration is not a system. You'll see a lot of demonstrations, and think about what they mean. What does it mean that ChatGPT produced an amazing essay about how to behave today? How much impact does that have on you? A little. Think about what we want for the future. We want the systems that will help us in narrow domains. How to do a surgery, how to invest, how to fly, how to run a robot in a company safely. And then one thing that I learned when I started to lead big teams, and I'm going to talk on Monday at the academia about it, is innocence in the team. stay innocent, and keep the ego very low. All the teams that have no hierarchy are bound to succeed. If you have strong egos, you're not bound to succeed. And this is a video. So as I mentioned, I work on an autonomous airplane. And this is a demonstration that we did on the airplane on a function that is considered extremely important in aviation, detect and avoid. So in the air, when an airplane flies, it can happen that another airplane comes in your way and you have to avoid it. And we know solutions for that. It becomes extremely hard if there are two objects. It could be a weather cell and an airplane, or it could be a balloon and an airplane. We worked with this with our pilots, and you'll see a demo, and you'll see people working on the system deployed on an airplane. Volume. Can you put up the volume?
To do flight testing of some really innovative flight software functions using neural nets to generate avoidance maneuvers in collision avoidance scenarios.
Machine learning algorithms, AI in general, require assurance. We want to know that the algorithms stay safe, basically, in the decisions.
Building trust that the general public actually has in pilots and shifting that trust to automated trust. How do we do that?
Head straight for it right now.
In our flight tests, we're going to have a neural net try to reroute our Caravan autonomy demonstrator around a second airplane that's headed right for us.
I got a visual.
This isn't something we're doing back end on the ground. We're doing this in real time on the plane. Hey, there's an intruder that's this many nautical miles away on this heading, and the AI will spit out, this is how you avoid it.
The system gives us a course to fly around the intruder and the weather.
We have a learned procedure which is optimal that avoids this airplane. Now we want to know that it stays safe in different conditions that cannot be anticipated.
The reinforcement learning itself is optimization. And from optimization perspective, it is a very complex task when you need to come up with a trajectory which would avoid multiple intruders.
It makes really intelligent decisions that pilots would make, and it's surprised us a few times with how it's decided to cut behind and then cut between the intruder and the weather cell.
Taking a point to the right.
There we go, it's loaded.
As the pilot, looking at these routes, you're like, wow, that technology is pretty exciting. It chose a path that I would have probably taken.
There is no other testing like this, and it's super cool to work on because we are doing this on a plane, we are doing this with other aircraft in the airspace, and we are pushing the limits of it.
Assurance technologies are maturing, and I think we're on a good trajectory towards having the kinds of tools, techniques, and processes we need to prove to ourselves, our regulators, and our customers that neural nets can fly safely on aircraft.
All right, off condition. Good job, guys.